Good afternoon, everybody. In afternoon, Anil is going to talk, and his title of the talk is Estimates of Bergman Kernel and its Applications.
So first, I'd like to thank Professor Biswas for this invitation to speak at this conference. And so the title of the talk, as she said, Estimates of Bergman Kernels and their applications. And so it's fairly analytic in nature, and it's mostly just basic, simple, complex, elementary complex analysis, and its applications study some problems in geometry and in number theory. So I'd start off with some general definitions of Bergman kernels. So I study the problems that I study using estimates of Bergman kernels and heat kernels. So recently, mostly Bergman kernels. And I'll start off with general definitions of Bergman kernels associated to holomorphic line bundles defined over compact manifolds, and the existing estimates, and then talk about my epsilon contribution in that aspect. And then that would be the first part. The second part would be just some notation and a slide overview of the analysis involved. And perhaps the interesting part would be the applications. So there are a few applications in geometry and in number theory. So notation, maybe I try to describe why I was interested in sort of these things, the motivation. I'll try to come up with the motivation in the second half of the talk. So let me first start with X being, so I start with general introduction, what's a Bergman kernel. So given X omega, any compact complex manifold, and omega a Hermitian metric. Let L be a holomorphic line bundle. That's with the Hermitian metric and the L2 metric. Then one looks for any Krigg k greater than 0. One looks at the space of global sections of H0x L tensor k. So again, we have the corresponding Hermitian metric induced by L and the L2 metric. So since X is compact, one can look at a finite dimensional space as dk, orthonormal basis of the space H0 X L tensor k with respect to the L2 metric. Then one can define the following function, dx L tensor k, z comma w, definition as sigma j runs from 1 to dk, si of c, and si. This is a function on x cross x, and one can, so the Hermitian metric L tensor k induces a metric on this as well, and one can talk about the metric induced by L tensor k on this guy. But this is a Bergman kernel associated to the complex manifold, associated line bundle L tensor k defined over the complex manifold X. And so a lot of people have studied it, a lot of analysis has been done on this. One of the main reasons why people are interested in such a thing, as one goes along the diagonal, tensor k, this guy essentially satisfies a polynomial in k power n, some coefficients, say 0, a1. And all these coefficients encode a lot of geometric data of x, like the curvature and several other things which I forgot. as right now, but this polynomial encodes a lot of data. So people are interested in studying the estimates of this guy. As this happens for k reasonably big, so the estimates that one has in this setting, a lot of work. It was initiated by Tian. It's okay. It's actually it's a holomorph. If you fix a W, it's a holomorphic section in this guy. If you fix a Z, it'll be a holomorphic section of. Okay, you can see this is a section of the bundle LZ tensor K tensor LW bar defined over X cross X. So this guy can be seen as a section over this guy. So yeah, so this is fine, I guess, as it is. So now a lot of work by Tian, Zeldich, Dumeli, a lot of people, and they've proved various versions of the following theorem. And I'll try to just give one simple version. And so X is compact. So one looks at the curvature form of just L. Locally, at any z belongs to X, one can write the omega, the natural one form on X, as dz1 dz j goes from 1 to n, where n is the dimension of X. Maybe I should have mentioned it here. It was always clear that n equals dimension of X. So you can write, so there exists a trivialization in which you can write your omega exactly like the Euclidean metric, and C1L will have the following form: sigma j equal to 1 to n lambda j one as following, and these lambda i's are called eigenvalues of the curvature form C1L. If all lambda 1 to lambda n are greater than 0, strictly positive, at a particular point z belongs to X, one can say the following thing: limit k tends to infinity, the Bergman kernel along the diagonal, this metric is inherited from L tensor K, defined over k power n. This is exactly lambda 1 to lambda n. This is the, so people have extended to several settings, and this is the most general theorem, which sort of people have different methods: Tian, Zeldich, Dumeli. People use heat kernel estimates. Some people use just microlocal analysis, but nonetheless, the result always turns out to be this. Okay. And on the non-compact setting, it's X non-compact. This was by Bergman. He doesn't even assume all he needs is X omega as Hermitian, and he has lim sup of k tends to infinity. So if at all it exists, if X non-compact may or may not exist, if at all this guy exists, it's C, this guy is less than or equal to lambda 1 to lambda n by k power n. This is the most general setting. This is the most general result when X is non-compact. So then a lot of work was done by Xion and Ma and Marinescu. They proved similar things, pretty much similar things, but X is symplectic, and furthermore, they could extend the estimates along the diagonal. They proved this is basically O of k power n e power minus root k dzw. So it's basically O of k power n e power minus root k into dx CW, where dx CW is the natural geodesic distance function on x induced by omega. And so this, motivated by this result, we, together with a student of mine, we put a the baby setting of Riemann surfaces, and L being the cotangent bundle, we could prove the following theorem. X is just a hyperbolic Riemann surface. Hyperbolic Riemann surface of finite hyperbolic volume. One can look at the cotangent bundle and look at the Bergman kernel associated to the k tensor power of the cotangent bundle along the diagonal. This was basically this is O of k, O of k by cos hyperbolic power k, the hyperbolic distance between z and w by 2. And one can check that this is slightly stronger than this minus root k. So it's a minor improvement from the existing thing, and I think this is also optimal. And the constant is also explicit. So this is when X is compact. X is compact hyperbolic Riemann surface. The constant is explicit. And it depends just on the injectivity radius of X. And when X is non-compact, prove that this is Ox of k by this cos hyperbolic power k, the hyperbolic distance between z and w, plus, so X is non-compact, but however it's a finite hyperbolic volume, so it will have finitely many punctures. Say P1 to Pn, so J goes from 1 to n. This is the parabolic Eisenstein series associated with each puncture, evaluated at 1/2. And this pi is a root k plus a constant times the root k. This is what we have, and it happens at the same time pretty much. Mahan and Marinescu could extend, they in fact they came down to hyperbolic Riemann surfaces and derived similar estimates, and slightly different from what we have, but however theirs was a lot more general, and so with this Marinescu could extend the same estimates to hyperbolic Riemann orbit surfaces. That is to say, they allow orbifold fixed points, whereas we do not allow orbifold fixed points. That's the difference, and they have qualitative estimates. This is more quantitative. One can really use this, as I'll show later. That this was very, very useful. All right. So this is all the story about the estimates of Bergman kernels, and now I'll just try to define certain things which are involved here, like the Eisenstein series and is some basic notation, and what really led me on this trail of estimates of Bergman kernels. Let's start here. Come to the second part, notation, motivation. So let X be a hyperbolic Riemann surface of finite hyperbolic volume. So complex uniformization theorem tells it's isometric to some gamma acting on H. So gamma is the Fuchsian subgroup. H is a standard hyperbolic upper half space, C equal to X plus Iy, and y greater than 0. Belongs to C and y greater than 0. And gamma acts in H. Gamma acts in H via Mobius transformations, and the quotient space is X. And we have the hyperbolic metric defined on H at any Z equal to X plus Iy belongs to H. The hyperbolic metric is given by the following formula: Z H Z bar by Y square, also dx dy by Y square. This guy's PSL2R invariant, it descends to give a metric on X which is compatible with the complex structure of X. And we assume it's a finite hyperbolic volume, so essentially it means it's less than infinity. Since there's a finite hyperbolic volume, the punctures of X are finite, which are in one-to-one correspondence with cusps of gamma. So cusps of gamma are basically fixed points of trace two elements of gamma on the real line. So yeah, this, and we assume there are no, so it's a Riemann surface, not an orbifold Obi surface, so there are no elliptic fixed points of gamma, or no orbifold points of X. Now, one can. So let's consider omega 1x, the space of cotangent bundle of holomorphic differential forms of weight 1. And it's a well-known fact that this guy, when one looks at the global sections of this guy, it's exactly the complex vector space of modular forms of weight 2. Forms of weight 2. And if just one goes a tensor, this corresponds to M2K gamma, modular forms of weight 2K. So I'd like to understand the metric on this from this space because I understand the space a little better. So any f belongs to, so essentially what it says, if I have any omega which belongs here, it's some f of z, dz, tensor k. Locally. In fact, this is a global thing because global section after all. Then one has a Peterson metric on mk gamma, Peterson pointwise, Peterson norm rather. And f belongs to m2k gamma. We have the Peterson norm. That's y power k after by UFFC. So one can use this and define omega, just the Peterson norm of f at the point C. Now one is interested to construct the Bergman kernel for this guy, but as such it may not be, since X is non-compact, with respect to this metric, it will not give. We have to go to subspace of this, the L2 normal sections. So let's consider it's 0 to x omega tensor k x. That's all omega belongs to x0x omega tensor kx, such that this integral omega with respect to the hyperbolic metric, this guy is finite. And this space exactly corresponds to the weight 2k cusp forms. The cusp forms and modular forms are, of course, of great importance in number theory, and one knows a lot about them. So on Sk gamma, one has the Peterson inner product, which is taken F and G. It gets you F times G bar. We take 2k, y power k, y power 2k, mu times C. This is always well defined because recursive forms. And one can look at orthonormal basis, F1 to Fdk. It's a finite dimensional space of Sk gamma. Let this be with respect to the Peterson inner product. And similarly, one can look at omega 1 so one can look at space at 0 to x omega tensor k. We have the L2 inner product induced by the Peterson inner product, and let omega 1 to omega dk be an orthonormal basis. This guy, where each omega I essentially f of z dz tensor k by 2 tensor k. So if one looks at the Bergman kernel for this guy, define it as the point. It's omega I z tensor wedge omega I and w bar, which is exactly the same as fi z fi of w bar this I goes from 1 to dk. These are the orthonormal basis of Sk gamma with respect to the Peterson inner product. So to understand the Bergman, so this is exactly the Bergman kernel. Let's call bx2k to be at the point z comma w, to be I runs from 1 to dk fi z fi w bar. This is called the Bergman kernel associated to the Sk gamma, the complex vector space Sk gamma. And if one observes, if one is interested in computing estimates of this guy, it suffices to estimate this guy, because this is exactly the Peterson norm of this guy, k to k zw, which is absolute value of this guy times y power k by 2 or y power k b power k, where z locally is x plus iy, I'm usi plus iv. Identifying x with its universal coverage, one can take z to be x plus iy and w to be u plus iv. So to estimate this guy, it suffices to estimate this guy. And I mean, accepting for the fact that this is just this, we have a lot more information in the sense, we do Freitag, one knows that this guy, bx2k cw, has the following expression: sigma gamma belongs to gamma, y 1 over z minus gamma w bar, C bar plus D power whole to K, where any gamma belongs to gamma with the form A, B, C, D, and this is the factor of automorphy here, CW bar plus D power K. So one has a series, and if one can estimate this guy, one can have estimates of this guy. And that's exactly what we have done, and they have in previous, and people have estimated this guy in different methods, or rather, at least along the diagonal. So maybe let me explain the motivation, why I was interested in estimating this guy. My initial thing started off trying to estimate this guy because it's a Bergman kernel for weight K cusp forms, and then this identification and the subsequent theorems of Mahan, Marinescu and all motivated me to write up the thing for the Riemann surface case. So why is this guy important in the arithmetic context? I mean, if you look at it, just any Bergman kernel, the reason it's important, it is basically it is the generating kernel for the vector space. So this guy is the generating kernel for instance, if one just taking F belongs to Sk gamma, one looks at the Peterson inner product, it plugs in F here, B2K x ZW, one half this integral, B power 2K F of W, F of W and Bx2K CW mu hype W. This is exactly equal to F of C. So this is it returns back the Z in the variable W. So if one wants to understand this guy using some basic functional analysis, it suffices to estimate to a certain extent only this guy. And there were results by Holovinsky, Blomer, but they assumed they worked with any F being Hecke eigen form, normalized, and they could say that the Peterson norm, if I remember correctly, it's sum of n power minus 1 by 37 times some k 5, I guess, 5 or 12, and where the underlying x is basically this is y naught n, the modular curve gamma naught n acting nh. In fact, maybe it's true for any congruent subgroup, maybe not, at least for gamma 0, gamma 1, I know it exists. Since then it has been worked out for several cases. This is something which motivated me to understand and estimate this guy. And but of course, for a general F, you don't expect as n tends to infinity, this guy goes to 0. One cannot expect such a thing for an arbitrary cusp form. And in fact, Ivanich is an example. It's just it becomes O of 1. But nonetheless, I guess using these estimates, one can say the same thing. And another big thing, one is interested in the Fourier coefficients of cusp forms. So any Fourier F basically at pi infinity, one can write this as A power n, Q power n. One is interested in the estimates of ANs, and Deline's famous bound for gamma to be SL to Z. We take any F belongs to Sk gamma. So, and you take the nth Fourier coefficient, it's n power k minus 1 by 2 plus an epsilon. And using our estimate, which is basically says this guy is let's basically just say for the sake of cos hyperbolic power k dh z w by 2. Naively, if just one integrates, if one just looks at 0, 1, 0, 1, computes the Fourier coefficients, and assuming this is all true, one gets exactly this. But there's a slight problem in the sense one jumps from one fundamental domain to the other, and the estimates that I had, I assume that Z and W are an X. So one can carefully manipulate the estimates over various fundamental domains. One can definitely improve upon as such, I'll easily give O of n power k by 2, which is somewhat, the trivial estimate, but nonetheless, the constant is very explicit, and it also works for any half integral weight modular form. So there is no assumption ever that k is an integer in all this analysis. So at least the hope is that a careful analysis might at least reduce it by some epsilon, which is not bad to start with, because you're working with any general f. And but some careful analysis estimates us jump from one fundamental domain to the other. So this was a motivation for me to come up with this guy, the estimates for this guy. So I just did not explain one particular thing, which was just the non-compact setting. If you remember, the Bergman kernel is essentially of x1 by cos hyperbolic power k dh z w by 2 plus x non-compact Eisenstein series. E belongs to the puncture set of punctures EP z along 1/2. I should just explain how they're defined. So if you take any P belongs to P of puncture, maybe rather we can look at it, which corresponds to cusp of gamma. One looks at gamma P, the stabilizer subgroup. And then you have a scaling matrix. Sigma P, which will take the cusp by infinity to P, and sigma P inverse of gamma P. Sigma P is exactly the set 1n01 and belongs to Z. One can define the Eisenstein series associated to a cusp P as sigma eta belongs to cosets of the stabilizer, imaginary part of sigma P inverse gamma Z power S, where Z belongs to H and S belongs to as a complex number. A lot of work is done here. To start with, this is invariant with respect to action of gamma. It defines a function on the quotient x, and this guy converges uniformly, absolutely and uniformly on compact subsets of H for all real part of S greater than 1, has a meromorphic continuation to entire C, and lastly at S equal to 1/2 has no singularities. I mean along the real line S equal to 1/2 has no singularities. So this was actually, estimating this guy was not a problem in the whole thing. All right, so this is all the motivation and all the players involved. And lastly, coming back to some applications. So basically 3 applications. We should just say how I do this sense. So I mean, one can just should do a little, one can, as I said, I use a series and I look at this absolute value. It's y power k by 2, v power k by 2, sigma gamma belongs to gamma, absolute value of 1 by c minus gamma w power k, and 1 by cw bar plus d power k. And this is, and one makes the following observation that imaginary part of any gamma w is imaginary part of w, which in this case is v by cz plus d squared. So this is w. And also known as the following formula for the hyperbolic function, distance function. This is absolute value of 4 times by v. Y is imaginary part of z and v is imaginary part of w. So using all this, one can say this is exactly less than or equal to the k factor I missed out. K times sigma gamma belongs to gamma, 1 by cos hyperbolic power k, get c gamma w by 2. So one basically breaks up into hyperbolic elements, given an identity, plus the parabolic elements. And this the parabolic elements, it's a standard technique. One can just estimate it by the Eisenstein series. And the hyperbolic ones would involve some invariants like the injectivity radius of x, which is Rx is infimum of dh c gamma z as gamma belongs to h gamma, all the hyperbolic elements, and z belongs to h. This is bounded from below. In fact, it's exactly equal to the length of the shortest geodesic on x. And one can have and the great thing about all the bounds are estimates are all stable in covers of Riemann surfaces, in covers. That is to say, if I have an estimate for x1, it's a fun degree cover of x0, then all the constants involved here are also are defined over x0, or they're bounded on x0 as well. So this was a good thing about it. This is all about estimates and all. And finally about some applications. So there are 3 applications, as I said. First one, you look at x any hyperbolic Riemann surface, finite hyperbolic volume, embeds in its Jacobian, the Abel Jacobi map. It's a complex torus. So you look at the normalized Euclidean volume form here, and then you pull it back. You look at Yuck. The hyperbolic Riemann surface already has a hyperbolic metric, and then you have something analogous to it. This we call the canonical metric, and this people found out it's exactly equal to sigma omega I of z, where h omega I z bar, where omega 1 to omega g. So the thing is, of course, g is the genus of x is greater than 0. So one has this pullback of the standard Euclidean volume form, and then that case is called the canonical metric on x. And this guy, so this can also be realized as, because of the identification of the cotangent bundle with weight 2 holomorphic cusp forms. That's exactly I equal to 1 to g, f of I z whole square, dz, which dz bar. This is I by 2g outside, complex square root minus 1 by 2g times this. And then one can ask for the ratio of these strings. You have 2 different metrics on x you want to compare. One is kind of analogous to the Euclidean metric. And this exactly what one would like to ask for, this supremum of z belongs to x. And it turns out this guy is exactly the Peterson norms. This thing, maybe I should j equal to 1 to g. And this has a lot of arithmetic significance. It arises naturally and bounding the Arakelov intersection theory of the self-realizing sheaf on. It started off with the observation x0n, and the first people trying to estimate this guy were Ulmo, Abyss, and then followed by Philip Michel, Akshay Venkatesh. So they had it in terms of n, so they could not get rid of the n factor. Some n power always remained. Then some heat kernel analysis and a very elegant argument, elegant geometric argument, Jorgensen and Kramer. They could prove that this guy, if you remember back, this is nothing but B2 of x of c, Peterson norm. There is some heat kernel argument, very nice one, and they could prove that this is exactly of 1 or Ox of 1, and the constant of course was invariant, and they could do it for any hyperbolic Riemann surface, especially for x0n. It was It was stable in covers, so extended being a cover of PSL dizzy acting on H. It was fun. So this was so this motivated for further study of BK, and with Friedman, Jorgensen, Kramer, they could prove, but they use a different kind of argument, more quantitative. Peterson, they could show this is OX of K3 by 2. Again, all the constants involved are stable in covers. All the estimates involved are stable in covers of Riemann surfaces. And our estimates also lead to the same thing along the diagonal. And they had two different methods, one both involving heat kernels, and so this was one was more recent, so one which is more quantitative. So much so. So these methods motivated me to work directly with the Bergman kernel and so the heat kernel. And finally, something, my little contribution when Professor Biswas asked the following question, together with Archana Mourier and Sen Gupta. He asked the following question. You can look at the symmetric product, you can look at the Cartesian product xd of xd times. One can embed this guy into the Picard group by sending any z1 to zd. This was sent to, just look up this map. Okay. OX of x1 plus xt. And this, of course, is also a complex torus. And when I, sorry? Oh, yeah, that's right. It's not an embedding. That's true. SimDX embeds into it. That's right. This map, and then you have the Euclidean metric identifying this with Jack X. You can get the standard normalized Euclidean volume form and look at its pullback under this. Look at the pullback. Let's call this map as phi star of New York. So one can define this. That's I by 2g whole power d. J goes from 1 to g. A comma b go from 1 to d. Have c, ca, cb bar, dza to h, dcb bar. So one asks this expression where this f1 to fg are essentially orthonormal basis of S2 gamma. Then one would like to study, let's call this as you can d, and one is just interested in studying you can d, the volume, the ratio of volumes, and it turns out that this can be estimated by dx2 at c raised to some what was 2d. We could derive optimal estimates of this ratio and then further prove on that simdx as an embedding. Simdx to this map x3 factors via simdx into picdx and simdx picdx being an embedding. And the last application, which is more recent. Let's look at x again hyperbolic, compact this time. It's also compact there. Compact hyperbolic Riemann surface. And one can get an embedding. Let's call this from simdx into the Grassmannian R comma n. Here, degree the following assumptions: C1 of L is assumed to be mu height pi 2 pi at any point C. Not really a big assumption. Then degree of L is assumed to be 2 into G minus 1. Right. Then fix k as any integer such that 2 into k minus 1 into G minus 1, this is greater than d. And then if one looks at the dimension of this L tensor k, Ox of minus z1 minus z2 minus zd, where z1 to zd are distinct points in X. This guy will be exactly equal to 2 into k minus 1, g minus 1 minus d. Some set duality involved here. And this will give us, so let's put r equal to 2 into k minus 1, g minus 1 minus d, and n to be 2k minus 1, 2k minus 1 into g minus 1. All right. And because the degree of L tensor k is exactly this. Then, so one has this map EKL, which takes sim dx. It's shown to be an embedding by Biswas before, which will map any z1 to zd to exactly at 0 x here, L tensor k tensor Ox minus z1 minus zd. This is an embedding, and then one has, so this is of course sitting inside 0x L tensor k. So one can see this is a vector subspace of this guy. So it gives you an element of the Grassmannian. And one has the natural metric on the Grassmannian, the Fubini-Study metric. And one would like to look at the pullback of the Fubini-Study metric and compute at any point z. And then after some calculations, we saw that this is exactly equal to I by 2 pi. J goes from 1 to d, to ci, the partial log of the Bergman kernel associated to the line bundle L tensor k tensor Ox minus c1 to minus z at the point c comma c. So this is in fact, so just estimating for one j equal to say, this is what's called the Bergman metric on X. So we computed the volume form associated to this. Let's call this as mu Bergman. And then we looked at its the ratio again with the hyperbolic metric, which also defines a metric on sim dx. I looked at the ratio. So this involved estimating the Bergman metric on X essentially, coming from the line model L tensor k. And this is more or less any arbitrary L. And after a lot of analysis, a lot of basic complex analysis, one can say something about the volume form by the mu hype, which gives a volume form over sim dx, and estimate this guy effectively and say it's k power 2d, some constant plus some small o of k, which goes to 0 as k tends to infinity. This has some importance in complex analysis, and so I'll stop here. Thank you.
Yes. If there are no questions, we will let us thank speaker again and